Cool.
Yeah,
Awesome.
should be going whenever you want to start.
Is my screen showing for everyone?
Yep.
Cool. Yeah, so today I'm going to be giving a pretty short talk on an introduction to text summarization and a bit about topic segmentation towards the end. So a bit about me. About a year ago, I started a company, Byrd.ai. So we actually specialize in meeting summarization. So I've been working towards text summarization for quite a while. Um, in terms of background, I'm pretty much self-taught when it comes to data science and machine learning. I did go to UCSD and get a BS in management science. So having that like math, economics, statistics background kind of helped, but didn't learn that much coding in school. Um, Before Bird, I ran a couple other companies, but nothing too tech related. So in terms of summarization itself, so Bird is a platform for meetings where we pretty much offer meeting summaries, smart filters, and we've been running a public beta for the past 6 months or so. So our AI assistant is able to join into calls, record and transcribe calls. And then at the end of a meeting, we send over a meeting summary where we basically take the meeting transcript and summarize it through various NLP methods. So I'll just be sharing a couple of those, but I think this talk's going to be a bit more introductory. So we'll start there. Yeah, a general outline. So we're going to first talk about text pre-processing for summarization, extractive versus abstractive, then a couple machine learning versus deep learning approaches, how to evaluate summarization models, topic segmentation, and then towards the end, I kind of want to open it up towards a discussion, and we'll talk about like the state of the art. Some of the state of the art is actually open source, so how you can apply it for any need. And if anyone's interested, I have some links towards some data sets where you can get started, and we can just discuss other applications of it. So starting off, there's always that pre-processing step for pretty much any other NLP problem. So to begin, you know the basics. There's cleaning, where you basically want to delete stop words, special characters, punctuation, and whatnot. And you want to deal with lemmatization, stemming. So you want to just deal with the root of the word, tokenization, and embeddings. So the reason is a lot of the machine learning approaches towards text summarization were very statistics based, and they had to do with the um, with the with the word count in each sentence. So when you don't do pre-processing properly, like when you don't remove stop words and whatnot, summaries are often summaries don't really work because stop words such as if, and, a, or, they kind of take over statistically in terms of they're most occurring. So there's no proper way to really get a good summary out of that. So cleaning is a really important step. Lemmatization and stemming also just helps with that, since a lot of the machine learning approaches really do rely on statistics of how often words show up and whatnot. This is kind of an example of what lemmatization is. It's similar to stemming, where you basically try to get the root of the word and you get a lot of, you just basically get its base form. So that's another step, lemmatization. Then when it comes to summarization itself, there's two main types. There's extractive summarization and there's abstractive. One is like trying to highlight things, and one is like actually taking notes yourself with a pencil. So extractive is more like a highlighter. It's easier to do, but it's not so easy to understand. What extractive summarization is essentially where you just highlight the key sentences or phrases in the text word for word. So the model isn't really predicting anything. It's more of a task of just predicting whether any sentence should belong in the final summary. So it's just basing sentences based on, it's just judging sentences based on their importance in the overall document. Whereas abstractive is a very different approach to summarization. Abstractive summarization is where a model tries to actually understand text and then paraphrase it in its own words. So it's like having someone actually take notes. it's a lot harder to implement, and it hasn't been too popular until recently due to new advances in like transformer models coming out. So we're going to be talking about both of them, but let's start with extractive. So there's two main approaches towards summarization. Like I said, the machine learning approach and the deep learning. So to break those two apart, the machine learning is more statistics based. Deep learning I would classify as more of neural network architectures. So let's start with the statistical approach. So when you use statistics to summarize text, as simple as it seems, like, oh, I'm just getting whatever, I'm just judging sentences based on their word frequency and word importance. It seems really simple, but it's actually a really effective technique. So there are three major approaches towards extractive text summarization when it comes to the machine learning approach. So the first one is a straight statistical approach, which I spelled wrong, but when it comes to that, sentences are scored directly based on word frequency, and the top sentences are basically selected. So for every sentence in a document, you score it based on importance, keywords, and the frequency of them, and then your summary is basically just the top sentences. There's also the semantic approach towards extractive text summarization, where you basically embed sentences with their own embedding, and that aims to actually get a deeper understanding of what the text is saying. And then the summary is actually picked based on other criteria. So when the model has a semantic understanding, if we were able to do more analysis, such as like cosine similarity between all the sentences, and we're able to look at the problem from another angle, and we can pick the most meaningful words based on their relation to the rest of the text and the overall text. And third is a graphic approach. So graph-based models were pretty much the state of the art for quite a while until the deep neural nets started to come along, when major transformer models were released by large companies like Bert and whatnot. So we're going to go through a couple examples of each of them and just explain how they work. But before doing that, let's go over the general outline and structure of what text summarization looks like. So essentially you have a text document. It can be how many ever sentences or whatever. You have that pre-processing. So a big important step there is that text cleaning, especially for statistical models. You need to get rid of those stop words and whatnot. Then depending on how advanced you want your model to be, you have some positional tagging. So for example, you can add your own features in text. Common features to look for, like distance between nouns in each sentence, how many verbs there are. So there's just a lot of features that you can really pull out depending on what you're going for, because the end goal isn't always just to have the end goal actually is to have the ideal summary, but parts of that will have to deal with like topic segmentation. You can segment different topics in a document with different position taggings. So that's kind of another pre-processing step. Then after that, in order for us to actually feed text into any model, we can't really just feed it raw data. So there's the part of tokenization and embeddings if that comes in, but we basically have to do something with those words. So we have to tokenize it, break it down into sentences and then words, and then feed that into a model. So tokenization is the next step. Then this kind of falls in for more statistical approaches. And before transformers, a common way to embed different documents was based on their TF-IDF. TF-IDF is essentially a statistical measurement that compares the word frequencies in each sentence to the overall document. So for each sentence, for each sentence, you're going to look at the statistical um, amount of words and whatnot. We'll go into the formula in a bit. With that, we calculate we basically pass that into different models, and we use that to judge what sentences we want in our summary. One thing to note with all these machine learning approaches is that they typically only work towards extractive summarization. There are ways to make them do abstractive, but they're just not that good, so I wouldn't recommend trying them. But when it comes to abstractive summarization, one thing to note is that there isn't a great way to really have summaries flow well, since you're essentially just picking out words word for word from the document and then just combining them. One thing that you're going to struggle with is grammatically flowing sentences and grammatically flowing summaries, and just having that smooth transition from sentence to sentence. That's something that struggles. So the first out of our three approaches is statistical summarization. So once again, that's mostly done with the TF-IDF metric. There are other metrics, but this is kind of like a baseline standard to start off with. So what TF-IDF is it's essentially a measure of the word frequency in each sentence as they appear in the document. So it's a pretty simple calculation, and it just ranks each sentence based on the amount of important words it has. You can have different ways to pick a summary, but essentially the two most common are just picking the top how many ever you want. So if I give it a summary of, let's say I give it a document of 10,000 sentences, and or let's say I give it 100 sentences and I just want a 5-sentence summary, I'll just say, give me the top 5 sentences based on their TF-IDF vetting. And that will be, that's one way that you can get it. I was going to go through the steps of creating a TF-IDF summarization model, but I felt like it was a bit basic. So I have a Google Colab notebook. I'll actually just link it here if anyone wants to go through it. I made pretty good comments step by step so you can understand what's happening. But instead of doing that, we're actually going to focus a bit more on the deep learning aspect towards the end. But yeah, that's there. I'll post these slides at some point. The next way for traditional machine learning approaches is based on semantic similarity. So the thing with the statistical approach was that the model had no idea what the words were really saying. It was purely just based on statistics and word frequency. A semantic similarity approach is a bit different because the model is actually trying to understand what the sentences are saying. So with semantic similarity models, we represent the words in meaningful vectors. So there's many different ways that you could embed words. There's bag of words models, there's word to vec, there's many different ways to embed words. Even you could just embed them based on their TF-IDF scores. But essentially what's happening is every sentence is receiving an embedding, and then you can rank your sentences based on different criteria that you want. So for example, you can do easier clustering, and you can measure the distance between centers of the clusters, or you can measure the distance between two different sentences, and you can use that to avoid getting duplicates in your summaries, which is a pretty common problem with other statistical approaches. TF-IDF kind of deals with that, since the word frequencies will cross out if it's their common, but other approaches that don't use TF-IDF, they struggle from repetition. So semantic similarity is a pretty good way to get around that. So here's an example of it actually being applied. So for each sentence, it's basically a point here. Each sentence was embedded and then it was plotted. And now and then there was clustering done. So this makes a pretty strong model because you can kind of pick how many sentences you want in each cluster. And yeah, so the way you would do that is, since now we have the ability to look at sentences semantically, we can look at the distance between the center of a cluster. So for example, for these blue sentences, these are going to be one topic, and we can pick how many we want. So one way would be to just pick the closest one or the closest 2 sentences to this topic, and then pick the closest 2 to this topic. So you can measure that distance by cosine similarity. There's other ways too, but cosine similarity is essentially a metric that just tells you how similar 2 vectors are. So if we have this green cluster of sentences here, and this gray larger point is the centroid of the sentence embeddings, we're able to calculate the distance from each sentence to its center. So that's kind of like which sentence best represents it. And then we can choose how many we want to pick. We can choose how many clusters we want. And those are all different machine learning approaches towards semantic search. There's a lot more you can do as well, but Typically, clustering is paired in with other methods as well, as it just kind of helps get clear clusters and pick how many sentences you want. But yeah, the overall approach with this, as opposed to just ranking each sentence and picking top whatever, is that you get to pick how many clusters and how many sentences you want in each topic. So that's the semantic similarity approach. The third machine learning approach was heavily researched for quite a while, and it's graph-based summarization, and it's a lot more complex. So now we're still doing a similar thing where we're trying to embed each sentence with a vector, but instead in semantic search, we basically just use the vector and only look at distance between it. For the most part, we're looking at the distance from the center to that, or we're looking at the distance from two vectors. For example, if we don't want overlapping information, we might not pick these two. We might set a threshold that the distance between two sentences has to be greater than something, so we don't have two overlapping sentences. But that's, for the most part, the limit of semantic similarity search, which is where graph-based networks come in. So instead of looking at distance between sentence embeddings in that sense, we actually create these nodes of sentences. And there's been a lot of research on different ways to do that and different ways to search through nodes, traverse through them. Um, there's just different ways to do it. And then when it comes to actually picking them, so once again, when we had the statistical model, our end goal was the summary is the top how many ever sentences we want. So the summary could be the top 5 most statistically significant samples. For semantic, it could be the top 5 closest to the center. But for graph-based, we have so many more approaches. So each node is going to be a sentence, and the connections can be whatever combination of features we can want. So a lot of features that are commonly engineered are things that look at like, okay, what is the distance from the nouns in every sentence and how many nouns are within X units and whatnot. And that's what determines the connections a node has. The more connections a node has, the more significant it is. And there's just kind of endless approaches towards how you can create these graphs. There have been a lot of models that still actually keep up with state-of-the-art neural nets. And it's just a whole different kind of approach from the deep learning method. And yeah, it's actually really, it's really, it's really powerful in the sense that it can also have its own way um, to send out its own clusters. So in semantic similarity, the way that we were clustering was essentially you can have clusters and then you can look at distance from them. Here we can do it based on different nodes, and there's different ways to alter the clusters, different integer linear programming routes to go through the graph and how to separate them. And yeah, it's just a way that people have developed to extract a lot more features out of their models. In my personal experience, I haven't delved too deeply in graph networks, but there's a lot to them. But yeah, essentially, that's how graph-based networks work. There's just tons of more features that you can draw out of text and transverse through to get your own summary. So that's a pretty solid overview of the 3 main machine learning approaches. There are a lot more. There's over 10 different ways. There's more ways that you can add features. But as of recently, there's been more of a focus on neural networks and deep learning approaches towards summarization. And in general, they're often better and they work a lot more for abstractive summarization. So once again, extractive was essentially where we're using a highlighter and we're just pulling sentences out of the, we're using a highlighter and we're just pulling sentences out word for word from the document. Abstractive is where neural networks really shine. In abstractive summarization, we're able to better understand what's being said and then rewrite it in our own words. A major benefit of that is the readability and the grammar and whatnot, and just the ability to make something that flows better. So yeah, that's been a big plus with neural network approaches. So here's how neural networks are here's how you kind of look at the problem when it comes to extractive summarization when you're building a neural network. So this quote sums it up pretty well. Extractive summarization can be defined as the task of assigning a label from yi equals 0 to 1 to each sentence, indicating whether the sentence should be included in the summary. So for those of you that know how neural networks work, essentially there's a lot more neurons that have more hidden layers and hidden parameters that we don't really know what they are. But just with the sheer size of their architecture, they're able to have more features in a sense to determine whether a sentence should be in the summary or not. And they don't really have to look at them statistically or whatnot. They just have more features. So in terms of extractive summarization, they've been doing really well. So it does get pretty technical in terms of what's going on to actually understand how to create and extend models towards what you need. For example, for us at Byrd, we have a really different use case where um, summarization models are often trained on a lot of data, but for us, we do meeting summarization. There isn't a lot of voice data, and those are challenges that you'll run into where there just isn't as much of the type of data that you need, and you need to really understand what's going on behind the neural network and what parts make it up. So it's pretty important to have a background in understanding first what's the task. There have been so many times where I've been experimenting with different models and just forgetting what the model is actually doing. It applies more to abstractive and how that architecture is. We'll get there eventually. But yeah, so the background is just to understand first the input of neural nets is different. So they will take in lists of numbers. So you have to find a proper way to embed your sentences as numbers for neural nets. The state of the art is basically flowing with transformers and attention mechanisms. So to understand that, you also need to know RNNs, bidirectional RNNs and LSTMs. Encoder decoder networks, they play a major role as well, especially in abstractive summarization. Then transformer models, but it's not that bad. You just kind of need to understand what transformers are, how attention works, and when it comes to developing models, one thing that I ran into was kind of needing to learn PyTorch. I learned all my machine learning data science stuff in TensorFlow at first, and then I started reading a lot of the state-of-the-art papers and research on what's actually happening with summarization. And then you find out it's all pretty much done in PyTorch. I think like over 95% of what I've seen is in PyTorch. So that kind of helps. The reason for that is a lot of the earlier transformer models, they were built with libraries for PyTorch, not TensorFlow. Although now it has changed and you can use the latest transformers on TensorFlow. When it comes to research that's being published actively, I still haven't found anything in TensorFlow. So if it's something you want to like really look into, PyTorch is pretty essential to understand what's going on in those models. And another thing with the background for understanding how neural nets do summarization is understanding a metric. So when it comes to summarization, there really isn't a good metric. So for the essentially majority of this talk, we started with the statistical machine learning approach of TF-IDF and explained how we would rank sentences based on the word statistical information. But that's kind of the metric that we use when it comes to evaluating our models, because there isn't really a great way to evaluate a summary. So some data sets out there that I'll share, they do have user-generated summaries. They have extractive, abstractive, they have pre-labeled summaries, but there just isn't a great way to measure how good your summary is compared to another summary without um, without like user suggestion and just preference. So that's a key thing to really look into is you can't always focus too much on the score. The common metric that's used is a Roche score, and it's essentially just a statistical measurement that measures the overlap of n-grams, and you can choose that, how many grams you want between summaries and the documents. So it's basically a statistical measurement of that measures how much of your summary includes um, n-grams that were found in the original document. So it's like comparing the tokens and documents to summaries, and you're just looking at how many there are. But yeah, it's important to note that even though you can optimize for that, a great summary doesn't always have the most statistical and lexical overlap. Sometimes we really prefer shorter summaries and we don't need redundance in summaries, even though that may achieve a better score in terms of what the model is being evaluated on. So that's just something to look out for. And when it comes to the actual architecture of neural nets for summarization, typically there's going to be embedding layers. So this is a Bert embedding, but this can be anything. It doesn't have to be Bert. There's just some embedding to convert your input text into numbers. And essentially that goes into whatever summarization layers you have. And then at the end, there's just a sigmoid layer. Sigmoid layer will be determining the sigmoid layer is just a 0 to 1 for every input, deciding whether it should belong in the summary or not. I'm seeing some people talk in the chat. If anyone has questions or
I
wants
was
to
just wondering about the Rouge metric, whether that does word engrams or
yeah, so
character engrams. So will it handle like misspellings or changes to spelling?
yeah, so there's multiple metrics. So when we look at the state-of-the-art performance, they're actually, here it is. They're measured in like N1 grams, N2 grams, N large grams and whatnot. So there's different.
And that's all within Rouge?
Yeah. So Rouge 1, Rouge 2, Rouge large.
Oh, wow.
Yeah. So, and these are state-of-the-art models and their scores. So they're evaluated on different Rouge. Yeah, it's pretty easy to recalculate. But yeah, I can't pull up the chat. So if someone else has something, bring it. Just say it. I guess I can't really bring it up right now. It's not
There's nothing else there.
cool. I see the notification, but I can't bring it up. So that's the general architecture. It's basically you have embedding, you do some stuff with that, and then at the end you have a sigmoid, and that's just does the sentence belong in the summary. Yet from it's just a sigmoid of 0 to 1. Yes, it does, or it doesn't. And yeah, that's kind of a thing with extractive summarization. That's kind of all you can do. You can determine whether a sentence belongs or it doesn't. The cool thing is these embeddings and these transformers here, they're actually massive models that were trained by large companies, Facebook, Google. They put out models that have literally billions of training data and parameters, and we can use those to get a really solid understanding of the language. So let's start to look into some of those embeddings. So Bert was a state-of-the-art model that was released a year or two ago, I think 2018. And it's essentially a model that was trained to be fine-tuned and later like adapted for transfer learning. So Bert is a model that was trained on a 3.3 billion word corpus. So it was trained on 800 million words of books and 2.5 billion word Wikipedia dump. It was trained for weeks on a lot of Google's TPUs. There's a couple different models they've put out. And what it's essentially doing is it's taking all the knowledge that it's learned through this 3 billion word corpus, trying to understand the language really well. So it tries to understand what is English, how does English work, and you're going to give it an input of sentences. It's going to give you its own representation of, okay, I'm the computer. Here's what I think this means. Here's some statistics about it. And here's kind of how it works. So you have a raw data set. These are going to be your strings of text. You're going to use Bert's tokenizer. And don't worry about this thing, just over it. This is a great image I found. But there are different transformer models. They kind of all work the same way in terms of their input. So they have a tokenizer, and what that does is you have an input sentence. It breaks the input down into tokens, and it uses its own vocabulary. So I think Bert has a vocabulary of around 30,000, and it breaks it down on a token by token. And I don't think I actually included any examples here, but what it's doing is it's getting its own understanding of your text, and it's broken down more than just word. it's broken down at more than a word level. It's broken down, forgetting the word, but it's broken down by different segments of words. So like running would be split into run, and then ing would be another token and whatnot. So it has a really vast vocabulary it's learned. It's able to understand your sentence. Then it goes through its Bert transformer layers. So it's basically 12 layers of multi-headed attention. You input your stuff with a couple special tokens, and at the end, it gives its embedding. So this is what the embeddings look like after it comes out of Bert. You have how many ever sequences you put in by 768 length vectors. So for each input, in this case, there were 66 tokens long. So they fed in 2,000 sentences that were truncated to 66 tokens. So a length of 66, 2,000 sentences, and what Bert outputted was a 768 dimensional vector representation for what it thinks each sentence meant. So that's a really large vector. It's gone through a lot of parameters, and that basically provides you with a baseline to start with summarization. So what this is outputting here is essentially a really well-trained model saying, okay, this is what this means in English and I understand it, and now you use that to do your predictions. So on top of these embeddings, there are some special tokens that Bert takes in and Bert takes out, and this depends on the model as well. But one thing is a CLS token at the start of a sequence. So a CLS token is essentially an aggregate of all the tokens before it. So if there were 66 tokens, the first token would essentially be a sum that would be able to represent all the tokens before it, and it can be used for stuff such as classification. So there are different ways that you can deal with Bert embeddings, but without getting too technical, a simple approach is just take the embedding, add a simple sigmoid classification, and you'll be pretty good. It'll be better than what state of the art was a couple of years ago, just that simply. Now, when it comes to what the state of the art is looking like today, people are using these transformers. There's a lot of them by different companies, and they're building their own layers on top of them. So let's look at what comes after the embedding. So this is essentially that embedding right here that we got. This is the embedding for each token. This is, and it goes through Bert, and then this is what's going now. So we've got these tokens, and we're going to do our own summarization layers on top of it. So there's a lot of stuff you can try depending on what you're trying to go for. So we run different models for different cases, and we have many different architectures built on top of the base embeddings, but there's just so many things you can do, from CNNs to RNNs to modify the embeddings. For example, you can add in certain tokens. You can add another CLS token at the start of every sentence to get more sentence representations. You can do stuff for document embeddings. You can add specific tokens to look at you can basically make your own features to compare like the CLS token to noun tokens to verb tokens and whatnot, and aggregate those into more layers. You can build your own custom transformers. So one of the models that I've linked to here, it's actually, it was state of the art for quite a while. It's still really well up there. Like it's a top summarization model, and they built their own transformer layers on top of Bert, and that's another route you can go depending on the way they want to do it. You can work with other transformers if Bert isn't the one. There's multiple versions of Bert. There's a Bert small, Bert large. Roberta is a bigger model made by Facebook. Albert, there's little Berts, smaller Berts. There's multilingual embeddings depending on what you're doing. But yeah, in terms of model architecture on top, there's just a lot of different choices you can go for. You can mix and match what you want, or a lot of the time, if you're not looking to make something state of the art and you just need a quick summarizer or something, you can just go with a simple sigmoid. You can also mix in other models, statistical approaches. So for example, you can use graph-based models to get clusters, use those clusters, get pass those through Bert, and then you find their summaries, concatenate them that way. There's just a lot of different model architectures that people have tried. When it comes to abstractive summarization, however, that's kind of what the new field has been, and that's what's been explored more recently and been developed. So abstractive is where you don't actually just copy and paste, because that's not really ideal depending on the situation, but there is a lot of grammatical troubles when it comes to extractive summarization. So abstractive is where the model actually tries to understand what the text is saying and give its own output, um, and like actually paraphrase it. So this is a little complicated. Maybe we can come back to if someone wants to read what's going on, but what's essentially happening is at every token that the model is, instead of predicting whether a sentence belongs in the summary or not for abstractive summarization, at every step you pass in the previous output plus the current token, and then you predict what the next token should be. So it's more of a sequence to sequence problem, and you're predicting the next token for every previous token plus the current state. So same thing with model architecture. Now it's sequence to sequence, so there's a different probability of what you're actually doing, what you're predicting. The input is a little different, since instead of just taking an embedding or CLS token or whatever, you're passing in multiple things. You're passing in the previous summary plus what's there now to predict the next token. It's doing that for every loop. You can modify the embeddings. Typically, that's what we've had to do for abstractive models. Instead of just giving it the CLS token, we've had to modify embeddings a lot. In terms of what they provide, the results are often a lot more coherent. Of course, they're more grammatically correct. And yeah, just in general, we've seen better summaries in that sense. They are a lot harder to do, though. So they do need more data. They do need more complex models. And yeah, so they're harder to make. So oftentimes going for extractive is going to be better, because it's hard to get a proper abstractive model, essentially just due to a lot of data issues and whatnot. But some tips to improve abstract models, abstract summarization that works most of the time is, a simple one is honestly to do extractive summaries and then abstractive. So do any form of clustering, get different clusters, do extractive summarization, and then pass that into into an abstractive model. So essentially what you're doing is you're finding you're basically doing topic segmentation. You're picking different topics in a document. You're first using extractive summarization to get the key sentences, putting those together, and then you're passing just the key sentences to an abstractive model to rewrite them and extract more from them. So that's another route that works. You can do a mix of that. You can pass that plus the original thing. You can build your own transformers for them. Graphical approaches have been pretty hot with abstractive summarization, where you mix graphical node similarity and whatnot into as another feature to the model. I haven't actually done that too much myself, but I've read a couple papers on it. And still at the end, you're still having that sigmoid. Instead, this time it's for the token it's trying to output. But that's kind of the big difference with abstractive and extractive. In one, it's kind of simple. You just give basically a model that has a really good understanding of English, a document, and it's going to be like, yep, this is pretty important. And in another one, you're giving it basically what it said before, but it's predicting everything token by token, trying to come up with what should be summarized. So it's a lot harder with abstractive, but depending on what it is, it works better. So some of the state of the art, it's pretty interesting how NLP is. A lot of the stuff is open source. A lot of the research is published, and a lot of the code is out there. So a couple places you can look if you're really just trying to implement summarization in anything. There wouldn't be too much of a point of building your own model unless you have certain needs. If you do, though, there's a lot of news data out there. So I've linked a couple here. But yeah, there is the CNN Daily Mail news set. It is 280,000 news articles. They have an average of 800 tokens. And on average, they're also all already summarized. Their summaries are about 50 tokens, and it has its own validation test set. So if anyone's interested in just trying it out, it's a pretty clean data set that's out there. GigaWord's another one, but for the most part, when it comes to summarization data sets that have summaries, it's going to be text-based. When it comes to figuring out what's out there, there's a great website, NLP Progress. It's not really always that accurate. I've seen there's a lot of stuff that just isn't updated on here, but they have different NLP categories outside of just summarization. So for example, speech recognition, machine translation, whatnot. But in this case, the one that I'm always looking at is summarization. So as Hobbs was asking earlier, yeah, they have different, the common metrics are based on 1 gram, 2 gram, and the largest n gram metrics. So there are a couple of different data sets and whatnot. And for a lot of them, aside from just the paper, the code is actually there if you want to implement it. The score is out there if you want to read it. So most of the work here is actually extractive, but as of recently, more and more abstractive models have been popping up. And if you look at the titles, you can see how much of a shift has come. Before, rogue scores were all in the 30s and whatnot. Now they're all like low 40s, but everything is pretty much using a transformer. Bert, another version of Bert, another version of Bert. And this is a pretty good place to go through the code and their articles. In terms of just implementing them, a pretty good one here is BertSum and PreSum. And they've made it all open source on GitHub. Their documentation is pretty solid to follow. But yeah, they're pretty high up there in terms of being state of the art, and they're pretty easy to implement. And yeah, another one that's not as high up, but it has its own benefits in terms of it's not trained only on news data. That was kind of an issue, is a lot of these are trained on news data sets, and that doesn't translate very well to real world applications, because when you look at news, essentially you have the introduction and the ending, and that's where most of the information lies. So for a lot of models, if you just take the first sentence and the last couple sentences, you're going to get a pretty good summary. But when you do something other than news, that doesn't translate through as well. So there's this service, Bert Extractive Summarizer, and a paper that follows it. And I haven't actually implemented it, but the guy that made he took an approach of using the Bert embeddings and graph models for training, but he trained it on, I believe, lectures. So if you want to read his paper, he trained it, I think, on Udemy lectures and different parts of speech tagging and whatnot. So if you're not really dealing with news and text and something else, this is a pretty cool one that's been trained on lecture summarization. So it's been a while since I read it, but I figured I'd link it, and it's really easy to use. There is a Python package for it, and yeah, it should be pretty straightforward to follow. But yeah, so those are a couple state-of-the-art models that are just out there if anyone wants to use them. But yeah, any questions or anything? I kind of want to open it up to a discussion towards the end.
Thanks for the talk. So I have one question. I don't know if you can answer, not related to Byrd. So you're doing some form of text summarization there. Did you start that by using the pre-existing data sets that you mentioned, or how did you get that going? Because it sounds like you're probably gathering data in your beta, but you probably had to have something that at least worked minimally just to start your beta.
Yeah, so my old company that I used to run, I had a lot of meetings and I couldn't honestly keep up. So I was kind of looking for a solution before I made Byrd of meeting summarization. And one of the things I was doing was just recording my meetings and our team meetings. So we kind of had quite a data set there of recorded meetings that we had internally that I was just using. So that helped. And then another thing was, yeah, we tried it with news data sets, trying their summarizers and whatnot, but it wasn't that great based on speech. And well, now we've had 2 rounds of betas and we've had many iterations. We have lots of models out there that we're always testing. But when it comes to speech summarization, it's a really different problem from text, because when you have meetings, there's oftentimes like random moments where someone says, oh yeah, that assignment from last week, I'll have it done like on Wednesday, and there's no other context, no nothing, but that's a really important point that has to be in the summary. We can't really skip over that. And the problem with speech transcripts is that they're not structured in any way. Like, as much as we could use other movies or whatever, there's audio data out there, but the fact that meetings themselves and the way that people talk in a meeting environment is so unstructured, that's been the biggest challenge for us. And like why we've had to make our own features and custom transformers and whatnot and just mess with models a lot, is because there's just not much structure towards the type of speech that we deal with. But yeah, in terms of how we started, we did try models of news, and that's why I have such a thing of all the models being with news. I was like, oh, I spent a lot of time learning this to find out that it's very news focused.
Cool. So are you gonna give us a summary of this meeting?
I would have. So we have different ways to have our assistant. So there's our assistant's name is Ali at Byrd.ai. Depending on the meeting host, it can join into the call and just sits there, records it. Depending on the host, we can get live transcripts and provide that as well. And then at the end, we'll send a summary. The host just has to set up a little step so we can join. But in terms of how we've been running our beta, you just invite it to your email once with Outlook or Gmail, and we'll automatically join every meeting that you have and send transcripts after. You have the option to send it to just yourself or the whole group at a meeting. But we've been like packed with our beta, so it's been fun. But summarization's a fun topic.
And can you post process the Zoom meeting like this meeting? Could you post process it once you have it recorded?
Yeah. But the problem with that is there isn't a great way for us to compare our summaries, because there's no like user generated there's no gold standard summary for us, and we don't like the ethical standpoint of creating our own summaries and going through people's meetings like that. So that's been another challenge. Like, as much as we want to go through them, there's no real gain for us to have like lexical overlap of summaries between meetings, because that's not at all what we're focusing on. Our problem is way more focused towards the random blurbs of like important information, the quick topic changes and how fast they go back. But yeah, we do some pre-processing, post-processing.
So if you ran it on this meeting and post-processed it,
We have our right now our beta, we allow clients to go through their old meetings. So we do more than just meeting summarization. So we have a couple like QA systems and whatnot where you can search through your old transcripts for things. So instead of just doing like a control F, you can kind of ask it questions and whatnot. But that's not as much of the focus right now. That's just kind of something that we have out there. But yeah, we do have all the transcripts, recordings, and stuff saved as well. And that's kind of another benefit for our customers.
Vibhu, question for the summaries. Can you tell the system how long or short the summary needs to be?
Depending if you're asking about us for Byrd or how the models work, depending on the model, you can. For most, you can. For us, in terms of how we've been beta testing it, depends on the team. So something we've run into is some teams are like, our standard is after a meeting, we send our Slack channel like a 4-sentence summary in this format, and we need it like this. It would be great if you could do that. Some others are like, oh, just send us whatever summary. So we've been testing the demand on that. There's a pretty split demand, but yeah, being able to set the summary length is possible in most models. So that's kind of, I wanted to give more of like a basic introduction, but when it really comes to these, like if you're doing just a machine learning based model, like a statistical model, and you're using TF-IDF, so as much as I said the summary is like the top 5, top 10 sentences, you don't really have to just do that. So as much as you're ranking every sentence, we don't have to take the top 10. Another common approach is to take the average TF-IDF score and say, I want everything that's 1.5 times greater than average. I want everything that's like 1.3 times greater than average. So that's kind of a dynamic summary based on how you want it. Because we also have issues internally of different meeting lengths. So it's really not ideal for us to set a target length. So for example, we don't want a 2-hour meeting to be condensed into 4 sentences. That's pretty hard to do accurately. But yeah, there's different approaches. So even like in the basic machine learning approaches, so instead of taking like the top, you can just take, I want something that's like 1.5 times the average, and that's a pretty good indicator too. And that's often because at the end you have a sigmoid activation that's just 0 to 1, and like you have that for every value. That's something that you can have user inputted as well. So like it's dynamically changeable, you know.
Okay, a follow-up question. So if I have a text that says that, you know, I lived in San Diego for a while, then I lived in Tijuana, then I lived in Los Angeles, I lived in Huntington Beach, I lived in Seattle. Is it within the reach of abstractive summarization to come up with a single sentence that says Leo has lived in a bunch of West Coast locations? Is that within the capabilities of it's a form of abstraction?
Yeah, I get what you're saying. Yeah, it actually is. So like if another example was like, I like to play basketball, I like to play baseball, I like to swim. It could be I like to play sports. So
okay.
yeah.
And then another follow-up question on that one. What if a statement, so those kind of words like Huntington Beach and Seattle and so forth, they appear in a lot of text as...
So I can explain why that is as well. So the embeddings that these transformers are outputting, so this Bert model that's outputting this 768 dimensional vector, right? So that can be used for similarity search and a lot of graphical searches. So if we look at um, this graph. So if you have like San Diego, Los Angeles, Huntington Beach, and whatever, it's pretty clear to tell that the difference between all of those is going to remain constant and that they are a city. And same thing with something else. So there's a pretty clear measurement there that's like, okay, this is all city. It doesn't matter where you're saying it when compared. And that's kind of another thing where if we look into the breakdown of what's actually happening to get these 768 units. So we have different models. We don't just use BERT. We use larger models that are like 1024 dimensions. We use a lot of models. And right now this is a 12-layer transformer. There's smaller, there's bigger. But in here, these all have multi-headed attention. And what that essentially is it takes every word and kind of gives it its own attention when encoding it. So it does a pretty good job at being it doesn't matter where in the text it was said, a word, and like if it's similar to something else, it'll still be able to figure that out. And that's just due to kind of how like large of an embedding that it is. It holds quite a bit of value. And the fact that it was trained on such a large corpus, and there are models a lot bigger than Bert as well, but this itself is like enough to do that, if I'm answering the question.
Yeah, I wonder about there's certain certain like words like the cities that are on the West Coast, right? They appear in a lot of text, which is allows this vectorization to capture the fact that they're on the West Coast. But there are other things like, say, you know, prime numbers, right? Like, I don't know, 101, I'm guessing, is a prime number, but I could be wrong. But not prime numbers that don't necessarily appear in a lot of text. Statements that involve those numbers could be abstracted if somebody picks up on that pattern, but the model will probably have a hard time. Is that a good guess?
So it's not actually even looking at numbers and words like that. So I don't know why I didn't include a code snippet of how the tokenization actually works, but the words are broken down at a n-gram level. So like the word hello, I think capital hello is actually not even one token. It splits it into two. So even if the word isn't in the dictionary, it can still get a pretty solid understanding. So like, I'll try to think of an example and come back to you, but there's a lot of words that can be broken down just based on the um, two parts of the word. Even if it doesn't know it or it doesn't hear it much, the similar words that would come from it would be able to represent it. Although I guess like prime number, I can't think of something off the top of my head, but just in terms of how much it's been trained and the fact that it doesn't look at stuff on a word level, it breaks it down past a word level and combines that is mostly enough for it to pick up on significance. We haven't had that issue of a word not being considered significant in that sense. And I'm pretty sure that's due to the way that the embedding is, the vocabulary is, the tokenization of it.
I have a question about the use case. So I know that you have been talking about the kind of text summarization for meetings. I would think that, like, for example, one of the use cases that we encounter in the research world is to, let's say, code search terms, right? Search terms in search engine. Have you used these kind of models on that kind of use case?
Yeah, a big thing we've been, what do you mean by code?
Like, for example, every single day, every single moment, there are literally millions of search terms being entered into Google and Bing. And so if from an analytical point of view, we want to say, hey, let's see how many topics are emerging from the search terms that people are doing. Let's say, are they interested in certain topics, right? So I would see some, like, the relevance of using what you're talking about here in that kind of use case to say, hey, let's summarize out of the millions of search terms.
So you're essentially building like a user mapping of their preferences and similarities between users and whatnot. That's done pretty commonly. So we don't actually have to use the outer embedding and like the CLS token itself. We can also just pull layers from Bert earlier. So we can just use this 768 dimensional vector as just a representation of whatever word we want and have it kind of, we can do whatever we want with it. And yeah, that's a great use for it. There's another slide I also thought I added of just possible use cases that I thought we could discuss, but
and also related to that, I'm thinking about Leo's question about numbers, right? In that case, for example, in a search term, I imagine a lot of people may put in zip codes, just straight zip codes. Would this kind of summarization capability be able to tell that's a zip code?
Yeah, just kind of based on the data that it's been trained on. We have a lot of numbers pop up in our meetings just due to the nature of business and whatnot. We've never had any issues with that. We always talk to our users and ask how stuff's going and whatnot, and we try different things, but that hasn't been something that's really ever been an issue.
Gotcha. Thank you.
So I just pulled up the chat. So Ian asked about the most useful resource or online course or book for NLP. When it comes to summarization, I read a lot of the just archive papers. I haven't had too much experience with the courses and whatnot, but if anyone else has or recommends them, yeah. When it comes to being specific for part of speech tagging, so a thing that we've been testing is allowing users to actually, or so Malia, did you mean that in terms of the more machine learning based approaches? Do you want to know about part of speech tagging for that, or for the neural nets? They're kind of different. Okay, well, for now, I'll talk about the machine learning approach to part of speech tagging. So I'm not the most knowledgeable about the graph-based approach, but the way that you can determine the node connections and whatnot, a common theme I've seen on part of speech tagging is like the amount of connections a node has is directly based on different parts of speech of its sentence and what it connects to. For example, like how many nouns are connected in the nearest n sentences and whatnot. So they go pretty deep in terms of part of speech. And for the neural network approach, you can always modify the embedding that goes in. So we've had to do that a good bit too. So what Bert gives out and what these transfers give out, what these transformers give out is the tokens that are embeddings for each word plus the CLS token, which is essentially an aggregate sum. But one thing that helped us kind of deal with that spontaneity is add more attention mechanisms on top of this that relate the CLS, so like the overall sentence meaning to each word, and see like, hey, why is this word popping up? Like, is it important? So that kind of helped us realize, like, even though this was sporadically said, nothing else in that sentence was like meaningful to a point where it gets a much more a heavier weight essentially, and the model can favor that more. So that's where like part of speeches come in for both. Yeah. So for Ian talking about how complicated it looks with PyTorch and whatnot, a lot of those state-of-the-art models on there, I can't even follow what they're going through trying to read them. They make it a lot more complicated than it has to be trying to do it in PyTorch. If you want to actually try to like implement any of these, I'd recommend using their Hugging Face transformers library and trying to just go at it with any of these data sets. So if you want to download part of this CNN Daily News dataset, it's pretty easy to set up the transformers. They have really nice built-in functions. So you kind of just have a certain input that you need to give it. So it's like this. You just kind of have to give it its proper token. So they have a function to convert each sequence into the proper tokens. Token goes into the model, and then it kind of just gives out an embedding. It's like a 4 or 5 line code process. It's just building the architecture on top that's more complicated, but it's like really user friendly to dabble in it, try it. Hobbs, you were talking about academic papers and blog posts and whatnot. With those models, there's a couple people that have been working on summarizing academic papers. There's one, I think it's like Science Bert, Sci-Fi Bert or something like that, where they're a team of like a couple people that are trying to summarize scientific doctor-based like medical papers. there's another one that does, I can't remember what type, but there's one that's pretty solid for medical papers. Blog posts, yeah, there's one that does Reddit stuff. There's a lot of these models out there based on the data and the availability to get it. Yeah. Anyone else have any other comments, thoughts, questions?
Yeah, I have a quick question. That was a great talk. Thanks. You mentioned that you don't really have a gold standard or the ground truth for your meeting summarizations for your company. So how are you like iterating on your models? Like, what do you use to?
So one thing that that was kind of an issue that really hit us, but we're able to, so we first started to offer live transcriptions so people would actually use our app during the meeting. And then we have a section for them to take their own notes, and we can kind of build that in. So if a user writes something themselves and it was like referenced in a transcript, oh, that's important. So we know that we need to work on that. Either our model got it and they just added it, but we can kind of use that as something that we need to have added essentially.
Hey Vibhu, I just posted a question in the chat. When you were talking first about like using Bert, you said, hey, you know, you could just take the classification token and pass it through a sigmoid. If I had 3 sentences that all sort of meant the same thing, wouldn't they then score? Like, and one of them was the highest score. So like, yes, include this in the summary. Wouldn't you just get 3 of the same?
So there are techniques. That's why I left this model building layer kind of open-ended, the summarization layer. So there's things such as trigram blocking, n-gram blocking that you can do to make sure that your summary doesn't have repetition in it. There's a couple different methods. For us, it's not as much of an issue just due to the erraticness of the speech, but for text, it actually is quite an issue. And a lot of, there's like 2 or 3 common approaches that text-based systems do. Trigram blocking pretty much, it works pretty well. It just kind of limits overlap. It's a pretty straightforward way that does that. But yeah, it's a problem that really comes up, but it had a rather simple solution.
And can you do the clustering technique that you mentioned with the statistical models?
Yeah, you can do that as well. You can even cluster the embeddings themselves and go that route and pick the NUI. The thing with the clustering is the clustering actually often has the most overlap in summary. So like if you were to pick like 3 sentences from here, let's say I wanted the 3 closest sentences from this centroid, I'm pretty sure those 3 are going to have a lot of overlap, you know? So this is where you'd actually need more blocking, because you ideally probably don't want these 2 right here, right? You probably want one and then one that's like X distance away. You probably want to set some threshold. So yeah, clustering has more of an issue with that. And then same with trees. You don't really want all the closest. That's where these, there's like a ton of different just integer linear programming. What are those called? There's just different ways to essentially section off different nodes and pick your clusters. So like it's common to go from this to a graph based if you have clustering issues.
Thanks.
Yeah.
Sorry, Vibhu, that was just a side discussion with Yuri.
I was like, I said, okay, no, it's fine. Yeah, anyone else have any other topics, questions, whatnot?
I think we're good on that. If anyone wants to ask a question, is it all right if they reach you
Yeah,
on
yeah.
Slack or put it in the general channel or
Yeah,
anything
anytime.
like that? Okay,
Yeah.
great.
Yeah. Thanks, guys.
Awesome, thank you. Can we get some clap reactions for him?
Indeed.
All right,
And I'll
great.
post those slides somewhere in the Slack or something at some point.
Thanks. I don't know if it's, I'm gonna try